Okay, so good morning. I am Aleksi Laukka. I am a doctoral student from the Prosessimetallurgy group here in University of Oulu. And by popular request, I chose to keep my presentation in English for further advancement of my studies. And my topic for today is high temperature corrosion during stainless steel manufacturing. This is a bit of an overview of all of the oxidation processes happening during stainless steel manufacturing, with some snippets of my research dropped in. So, as you may or may not know, the popular ingredients for stainless steel manufacturing in Finland are ferrochrome ore, or scrap, or lots of scrap. But in the end product is usually a strip coil, as shown in the right here, or strip plates, or something like that, strip wire. And the process to produce this stainless steel in Finland, and this is the Outokumpu Tornio Works process for stainless steel strip coils. And this is shown from casting onwards. We have the hot rolling side and cold rolling side. And you may have known that before the stainless steel is delivered in its shiny, lovely state, as shown in the right here, it has undergone some oxidation during the processing, as shown on the left here. And the oxide layer is produced and removed many times, and it's different thicknesses and different consistencies during the processes. And when we have a metal and an oxidant and high temperatures, we get accelerated corrosion. And owing to their namesake, stainless steels are metal alloys with a primary focus on corrosion resistance. And the alloying elements in stainless steels contribute to the formation of a complex oxide layer, or a scale layer. And this complex oxide layer is better than a simple oxide layer when attributing for the namesake of corrosion resistance in pretty much any environment. But the complex oxide layer is somewhat not so good as a simple oxide layer when studying what contributes to the actual improved corrosion resistance. And here we have a oxide permutation chart for a binary AB system that shows all of the possible outcomes for oxidation when we have only two different things. And this is shows all the physical and chemical properties that can affect the forming oxide. And here we have a composition chart for a pretty normal austenitic stainless steel. So there are quite a lot of oxidizing or things that can oxidate. Here is the same process chart as before. So we have the hot rolling and cold rolling side. And shown red, on red circles here, we have places where oxide scale can form, and black where oxide scale is removed in some way, or one way or another. So we have, we're starting from the left here, we have the casting. We have the slab coming out of the casting machine, and it is put to the walking beam furnace prior to hot rolling. Both of these processes produce oxide scale. And we have the roughing mill that removes, or before the roughing mill, some of the scale is removed. And before Steckel mill, there's another descaler, and we have the tandem mill and Steckel mill on the hot rolling side. Both of these processes involve oxidation when the process is in operation. On the cold rolling side, we have the tandem mill and annealing that produce. Tandem mill, not so much. There is a preheater oven, but it's not so used. And the annealing of furnace before skin passing mill. And on the cold rolling side, we have electrolytical and chemical pickling, as well as mechanical descaling, but the mechanical descaling is not used on final pass cold rolls. As for high temperature corrosion and what actually contributes to the oxide scale formation, we have the atmosphere, we have temperature and holding time. And throughout the process, as we saw, we have different atmospheres, we have different holding times and different heat profiles where the temperature changes. So for the cast, we have atmospheric as well as for hot rolling. And for walking beam furnaces and line reheating is the annealing furnace on the cold rolling side. We have a burning agent producing an atmosphere that contains water vapor, which further increases the oxidation rate. As for holding times, after casting, the variance can be large. The slab is let to cool down, and it can take between, let's say, hours and days when it's either stored or put to the reheating furnace. For the walking beam furnace, we have 3 hours. Hot rolling is 5 to 10 minutes. Change depends. Line reheating is for 1 minute to 10 minutes. Under normal operation, we can have line stops, but we don't discuss that here. And for heat profiles, we have cast slab that cools down from 1300 Celsius to room temperature, even not that fast, but it can be done. And for walking beam furnace, we have a heat up from between either a stored slab or a directly charged slab to the furnace. It heats up to 1100 Celsius to 1250 Celsius. Depends on the steel type, of course. We have hot rolling that is constant from 900 to 1100. And we have line reheating that is also dependent heavily on the steel type being produced. So we have different heat ranges. And here we have an image of a line reheating oven that has different zones for the heating. As for oxide formation, how it actually happens, this is just a short overview. We have, of course, the chromium diffusion, the surface, the formation of chrome oxide or chromium oxide. This leads to a chromium depleted layer to form below the oxide. So that's the alloy, the metal alloy that has lower chromium content than the actual allowed amount. And the metal, as the oxidation progresses, the metal and oxide ion diffusion through the formed oxide layer contributes to the formation of a multi-layered structure. And the ion diffusion speeds affect the oxide layer formation and type. So when we have a slow diffusion and thus oxidation rate, we have a more protective chromium oxide layer and spinels involved. When it's fast, we have less protective iron oxide layer and spinels forming. And when we have high variance in these diffusing metal ions inside the layer, either perpendicular or cross sections, we have pores forming inside the oxide layer. Now, if any spallation or cracking happens during oxidation, the oxidation rate increases significantly because it exposes the chromium depleted alloy layer to atmospheric or gaseous atmosphere. And the end result is an oxide layer or scale layer. And the oxide layer properties are its thickness, the porosity, and morphology. And morphology covers the overall look of the layer, and it has includes all compositions of the different oxide phases, how the metal is composed in the layer, and such. And these are all affected by the steel type, the holding time, and the atmosphere. And part of the oxide layer forms on the top of the steel through cationic transfer of ions. So we have the original steel surface going here, and the iron layer grows atop of it. And below the original surface of the steel, we have an inner oxide layer forming that is a result of anionic transfer of oxygen ions through the scale layer itself. And so what we actually research considering this oxidation of different parts of the processes and what can be done about it. We have constraints set upon either by manufacturing processes or the end product qualities or properties or such. Or I like to call them more of opportunity windows. So the steel standard is set by some standardizing body, but it has some leeway in how the compositions are worked. So there's some compositions you can change without going out of the standard. We also have the temperature. It's usually an aim to have some temperature, but it's mostly affected by the subsequent processing of what the temperature actually can be. So we can play a little bit with the temperature also. We have the holding time, so how long the process actually takes. So as I said earlier, the annealing furnace in the cold rolling side, it can vary from minutes to 10 minutes. So there's some leeway there. Also the atmosphere, this is pretty standard to have an atmosphere that is produced by some combusting or burning agent. But if you change the combustion agent, then you have a different atmosphere. So as for some research results, we have here an fairly standard AC304 austenitic stainless steel. This is the same steel I showed earlier on the composition chart in a H2O containing atmosphere for 3 hours. So we have the time scale here. So here's 3 hours. We have the temperature scale here. We have 1100 to 1250 Celsius. And we have the scale formation amount in kilograms per square meter. And it would be fairly logical for an oxidation process to follow a linear behavior where you increase the temperature, the oxidation amount increases. But we have like these aberrations to this. So we have around 0.2 kilograms per square meter forming here. And it actually decreases when we slightly increase the temperature by 25 to 50 degrees Celsius. And this has the result. The reason why this happens is because of the diffusion differences between different elements like chromium and Si and such, that they change due to the temperature. And here we have the same steel as before, but now it is microalloyed with either 35 ppm boron or 55 ppm boron in either oxygen or water vapor atmosphere. So microalloying is the practice of changing the alloying amount of a steel in such a way that it still fits inside the standard it is supposed to be. So what we have here is a difference chart of comparing, of going from 7 ppm boron microalloying to 35 or 55 ppm microalloying. And we see that in some temperature ranges, the differences can be as high as 60% less or 120% more. And this also has linkages in the way that the different alloying elements interact with each other during the oxidation process. So usually it is so that when the oxidation rate in the beginning is higher, then you have a little less forming later on. And boron is linked to having, or when we alloy a little bit more boron, it segregates to the grain boundaries and inhibits the grain boundary diffusion of some elements. As for atmosphere, here we have an AC304 again in H2O atmosphere. So this is H2O that it's not full H2O, but we have different amounts of H2O. The rest is nitrogen, carbon dioxide, and some oxygen, I believe 3%. So this is a study to see how changing from propane burn to methane burn affects the scale formation in a walking beam furnace. So for a propane burn, we have the 13.1% oxygen containing atmosphere, and when we change it to methane burning agent, we get the 16.1% oxygen H2O atmosphere. And we see that the oxygen scaling amount increases slightly by around 20%, but it actually is beneficial because in addition to increasing the scale formation amount, the porosity in the steel or inner oxidation layer and steel interface increases, so the scale removal is easier. And here we have a microscopic study of the AC301 stainless steel with boron and molybdenum microalloying. We see that changing the microalloying a little bit, I think this 7,300 ppm molybdenum is right on the border of the standard. So we see that increasing the microalloying amount produces a varyingly different scale layer, and especially the interface between the scale layer and the steel substrate. So this is like an broken off the scale layer. This is actually an epoxy here, this black area. And some practical applications from these oxide formation studies have been the walking beam furnace operation parameter optimization. So instead of using the walking beam furnace in a way that if you put austenitic stainless steel, you use this program, or ferritic stainless steel, you use this program, we have, for all of the austenitic stainless steels, we can use different programs based on the studies made by our group here. Also, we have the oxide morphology improvement through microalloying, so it can be seen if it's easier to remove scale. For example, we have an ongoing research on stainless steel strip pickling optimization, and we have the end product surface quality improvement as an aim for our research. Some business ventures have been the slabcast simulation and manager ideas, scale formation package. So this is linked to a casting machine simulation product. And we have the stainless steel strip temperature measurement by strip metal and oxide emissivity coming up later next year. So thank you, and yes, thank you.
Thank you, Aleksi. Very interesting. Is there any questions? Okay, I have.
Okay, thank you. Please.
At first, what kind of there is always coming this scale layer to the steel surface. What are the main disadvantages when this scale is formed to the steel surface?
Well, those are, I would like to call them properties, because you cannot make it not come to the surface because of the furnaces used. So the disadvantages can be, I think there's mostly linked to how the scale layer is, or what happens to the scale layer, because if the scale layer is consistent, it's good because it protects the steel beneath. But if there's spallation or cracking, we have these areas in the steel surface, even if the oxide layer is fully removed, we have these scale layers or areas in the alloy surface that are depleted of mostly chromium, so they are prone to further corrosion in their actual application environment. So we have pitting corrosion, resistance goes down usually, and if the scale layer is not fully removed, we have like a in-rolled scale, which is a surface defect, a very serious surface defect, especially on longer product deliveries. They cause high damage to the company.
That was very interesting that you mentioned this inner layer oxide scale. Is it so that it stays there, or can you remove it?
It actually gets removed mostly from the steel substrate and the inner oxidation layer interface. There is some variation, mostly linked to the porosity. If there's porosity near the interface, then it's easier to remove fully. Yeah. But if it has like these tendrils of metal in the near vicinity of the interface, then it's harder to remove and easier to get rolled in scale.
Okay. But is it removed by pickling, or can you use descalers or something?
It depends on the process phase. So for the walking beam furnace, we have this water jet.
Okay.
So
it's enough?
Yes, it's enough, because the thermal expansion coefficients are so different between the metal alloy and oxide.
Okay.
And further in the process, we have picklings and mechanical descalers and such.
Kiitos, Aleksi.